Hello everyone and welcome back to chemistry. In this video, I will be discussing dot point 6.1, which is the common features and operation of an electrolytic cell. Before we start, let's just do a quick recap of what we've done last term. So we looked at galvanic cells last term. Just a reminder to everyone that a galvanic cell is essentially a device that converts chemical energy to electrical energy. So you generate a flow of electrons. And there are three types of galvanic cells that we looked at last term: fuel cells, primary cells, and secondary cells. Primary cells, just a fancy way of saying your regular battery, your regular AA battery that is not rechargeable, so that when the reactants are depleted, you need to discard the cells. Secondary cells are essentially rechargeable batteries, so your phone batteries, your laptop batteries. We haven't actually looked at the recharging process, and we're going to look at it, I think, next week. And I think the main cells that we focused on last term were actually fuel cells, which allows you to generate a constant output of electrical energy or electricity as long as you have a constant supply of reactants. And this is due to the way that the cells are built, that it allows more reactants to go into the cells when you need them to be. Now, galvanic cells actually under a bigger umbrella of what is called an electrochemical cell, which is essentially a device that allows you to either go from chemical energy to electrical energy or vice versa using a redox reaction. You cannot have two processes at the same time, but you can either have chemical to electrical or electrical to chemical. So I think you can kind of guess where an electrolytic cell is going to fit into this picture. Electrolytic cell is essentially a device that allows for the opposite conversion. So you're going from electrical energy to chemical energy. Now, why would you ever want to do that? If chemical energy is the output, that's just a fancy way of saying that you want to produce some chemicals using electricity. So you're not trying to provide electricity, you're trying to produce chemicals by supplying electricity. And we're going to look at some specific examples later. All right, so this is a very simple setup of what an electrolytic cell may look like. And I think you can see, I'm going to change the colors, it's not as dramatic. So you have a power supply. This is very, very important because electrical energy is your input now. So if I'm just going to write that again, you're going from electrical to chemical energy in this case. So you need to start with electrical. So you need to start with a power supply. So I'm going to try to redraw this into a schematic diagram, which is the form that we're going to use when we analyze electrolytic cell. I don't think we can draw this. Well, you can try. I'm not going to do it because I don't think I can do it very well anyway. So that's my power supply. See, virtually identical. You do need to show, and I think it shows here that the power supply is connected to the two electrodes. So we're going to go, let's say this side is connected to one electrode. Wow, look at that. Okay, let's try again. That's not even any better. And the other side is this electrode. So the first essential feature, what even is this? The first essential feature is a power supply. The second essential feature would be the two electrodes. I don't even think that's any better. I'm going to stop redrawing a rectangle. It's very hard to draw well on this really low quality, cheap writing pad, but anyway. And then you can also see that the two electrodes, which in this picture are the two black hooks, or whatever they are. Oh, we'll talk about this in the future. Okay. Anyway, the two electrodes are submerged in a solution, so you do need a solution still, and that's your electrolyte. Every time I draw an electrolytic cell, it reminds me of like a face. You have like the eyes, and then there's anyway. Please tell me I'm not the only one who sees that. What on earth even is this? Okay, this is not good. I'm trying to draw a beaker, just in case you can't tell. All right. I'm gonna stop because I don't think it's gonna get any better. So that's your solution. So three essential features: electrolyte, which is the conducting liquid, most of the time in the form of an ionic solution. But essentially, you just need anything that allows for flow of charged particles so it could conduct electricity. So this is your electrolyte. We're going to talk about some solid electrolytes in the future. That'll be fun. Your two electrodes are here, and this is the power supply. I think this is also a good time to talk about which electrode is the cathode and which is the anode. All right, when you draw your power supply, you have to label which side is negative and which side is positive. So if you go back to that picture, I think you can actually tell that that's the negative terminal of the power supply. So the negative terminal is connected to one electrode and the positive terminal is connected to another electrode. And this is going to be very, very important because if this electrode is connected to the negative terminal of the power supply, it means that electrons are coming out of this terminal into this electrode. So this electrode is gaining electron. And if it is gaining electrons, it is going to be the side of reduction because reduction is gaining electron. So it's going to be the cathode. Gain electrons, side of reduction. So this is your cathode. So in the case of an electrolytic cell, you can identify whether an electrode is the cathode or the anode based on the terminal that it is connected to. Well, the terminal of the power supply that it is connected to. Similarly, this electrode is connected to the positive terminal of the power supply. So electrons will be forced to leave this electrode because electrons will be attracted to the positive terminal here. So this electrode is losing electrons and oxidation must be happening on this electrode. I'm not saying that the electrode itself is losing electron. We'll talk about that. That's like a whole other thing. But the process of losing electron is happening on the surface of this electrode. So this is going to be your anode. Okay, so the anode is going to be the electrode that is connected to the positive terminal of the power supply, and the cathode is the electrode that is connected to the negative terminal of the power supply. One more thing to point out is the actual polarities of the electrodes. Because the cathode is connected to the negative terminal of the power supply, the cathode is going to be negative as well. And because the anode is connected to the positive terminal of the power supply, the anode is going to be positive. So hopefully you can already tell that the polarities of the two electrodes in an electrolytic cell is the opposite of what it looks like in a galvanic cell. The cathode is negative in this case, and the anode is positive. And the reason for that is because these electrodes are being connected to an external power supply. There is an acronym that I came across the other day because I don't actually use a lot of acronyms. I know you guys like acronyms, guys and guns, other people like acronyms, but yeah, all right. So I'm gonna try to incorporate more acronyms in my teaching. But the acronym that I saw the other day was panic. So whenever you see an electrolytic cell, you should panic, which essentially means positive anode and negative cathode. Not sure where the I comes in. Cathode is negative. Anyway, panic. Or just use common sense, whatever works. So that's the essential features and the flow of electrons. All right, so this is just a summary of what I just said. You don't have to be too concerned about this particular notation for the power supply. I'm not going to ask you to draw it. This is anyone who does physics would know how to read it, but I will always tell you which side is supposed to be positive and which side is negative. Even though this is horrendous because it's actually in the opposite direction of what I just drew. But anyway, this is another summary of what I just said. If you want to write the notes down, so you can pause here or look at the PowerPoint. Okay, so let's talk about what actually happens in an electrolytic cell. And the process that happens in an electrolytic cell is called electrolysis. Makes sense. Yeah, okay, so that's what I just said. And The definition of electrolysis is a process that uses an electric current, to bring about a chemical reaction that does not occur spontaneously. So this is the second main difference between a galvanic cell and an electrolytic cell. The first one was the difference in polarities of the electrodes, and the second one is the reaction that actually happens in an electrolytic cell is non-spontaneous. Because it is non-spontaneous, you need to supply electrical energy for it to happen. And the reason why you actually want to do that, I've recorded this video so many times, I can't remember whether I've talked about why you would want to do that, but some applications of electrolysis would be things like extraction of metals. So you really want to produce chemicals here. You also want to recharge batteries, which is essentially a process of reproducing the reactants, or electroplating. And we're going to look at these specific applications next week, I believe. But there's a reason for electrolysis. But the reason is not to produce electricity. All right, let's give you one example, and I'm going to give you so many more examples in future videos, but let's just think about how it actually works. So let's say I have an electrolytic cell that is made from this solution. The electrolyte is 1.0 molar potassium nitrate, and there are two electrodes. They're both carbon, which is another way of saying that they're inert, so they're not going to participate in the actual reaction. And then you have an external power supply. So we're going to try to draw a schematic diagram of this electrolytic cell from the information given. So power supply, okay, and then I'm going to connect this to the two electrodes. You know, one of these days I'm going to get better at drawing these, but it's not today. Should have done this actually. Look at that. Can I say it's artistic? Okay. You do want to kind of leave some gap here so that your beaker doesn't look. Just ignore what I just said. I don't even know what I'm talking about. Okay. I don't like this, so I'm going to try that again. If you have a pencil, that would be so much easier. Okay. All right. We're done with the drawing. So we have 1.0 molar potassium nitrate in the solution. Always include state. And let's just say that's negative. So that's negative. This is carbon solid, and this must be the cathode because it's connected to the negative terminal of the power supply. This is connected to the positive terminals, also solid carbon is going to be the anode. Okay, the question that we probably want to ask is, what is going to happen if I do this setup? I just mentioned earlier that an electrolytic cell is normally used to produce chemicals, so what chemical is going to be produced here? Now, in order to answer that question, and I'm going to make like an entire video on this topic, but just for this example, you're going to need your electrochemical series. So this a snapshot, and we're going to think about what species are actually present in the first place. So the carbon electrodes are inert, so I'm not even going to worry about them. So in the solution, you have potassium ions, you have nitrate ions, and because this is a solution, you also have water. Nitrate ion, you're not going to be able to find on the electrochemical series. It's almost always treated as a spectator ion, and I think I actually haven't seen an example when it's not. If it is not an spectator ion, the question will have to tell you. So you don't have to worry about nitrate ions. Potassium ions here, and then let's find the water. So there's a water here, and then there is a water here. So you can clearly see that you don't have a spontaneous redox reaction with this reaction mixture. There is no backward Z being formed. However, the point of an electrolytic cell is not to have a spontaneous reaction. Out of the two oxidizing agents, this is the stronger one. So this thing is going to go forward, and this thing is going to go back because electricity is supplied. So as we mentioned earlier, electrolysis is a process that uses electricity to force a non-spontaneous reaction to happen. So the reaction will happen in this case between this and that, and it will form an actual Z because it's non-spontaneous. And the reason why the reaction happens is because electricity is supplied to it. So this is reduction. So at the cathode, what you're going to have is H2, this reaction. Well, we'll see. Okay, so you're going to have 2H2O gaining 2 electrons from the power supply to turn into H2 gas and 2 OH minus. Okay, so essentially electrons from the power supply is going to go in here. The water, which is in the solution, is going to receive these electrons and get reduced, and you're going to see hydrogen gas being produced from this electrode. It's going to go up, and then there's some hydroxide ions being released as well. If you have a pH indicator, you should be able to see a color change around this electrode. Oh, this is a time when I actually want to do an experiment. Okay, talk about that later. Now on the other side, this water is going to lose some electrons. So the water around this electrode is going to lose some electrons and get oxidized into oxygen gas. It will also produce some hydrogen ions and some electrons. So oxygen gas will come out and hydrogen gas will come out. Oh, sorry, hydrogen ions will come out as well. The hydrogen ion is going to go towards the cathode because it's negative, and the oxygen, the hydroxide ions will go towards the anode. But we'll talk about ion flow probably next week as well. So essentially, the electrolysis of 1.0 molar potassium nitrate, it's going to produce two chemicals, hydrogen gas and oxygen gas. That's an example. I'm just going to draw electrons going up here. Okay. One more thing that we need to discuss is the voltage required for electrolysis. Once again, the main difference between electrolysis and galvanic. Galvanic would produce electricity, and you can calculate the voltage that a galvanic cell will produce. So the opposite process, which is electrolysis, you need to be able to estimate how much voltage you actually need to supply to the cell for the desired reaction to take place. So we go back to this example. The voltage here is 1.23 and the voltage here is negative 0.83. So the difference in the voltage of the two, I am actually using a calculator because I'm really not in the mood of doing anything. I'm a math teacher. Anyway, let's not go there. So the difference in voltage, what do I even have on this slide? I don't know. Okay, I don't have anything useful. So 1.23, now let's use the other one. The difference between these two is 2.06. This gap is 2.06 volt. But if you want this non-spontaneous reaction to occur, you actually need to supply a voltage that is a little bit higher than 2.06, because when you supply electrical energy, not 100% of the energy is going to be converted to chemicals. So some of the electrical energy from the power supply is going to be lost as heat or sound or whatnot. So you're going to need something more than 2.06. So let's say 3 volt or something like that. Just don't, okay, you can do 2.07, but maybe don't do 2.07. I say 2.5 or 3, so voltage required. You want to make sure that it's definitely higher than the difference in voltage between the oxidizing and reducing agents, just to account for heat loss. So let's say 2.5 could be that. I'm just going to write here that it has to be greater than 2.06 volt. Okay, that's just me explaining that. And I think that's it for this dot point. So we're going to talk about flow of ions later, but hopefully if you read this, you can identify the common features, you can describe the common features, and you can describe the process oxidation and reduction, and the flow of electrons and the required voltage for an electrolytic cell.